So here's the real number line. We've talked before about finite sets, but in fact the real number line is an infinite set. There's a ridiculously large infinite number of things on this. Now there's a lot of subsets of this which are also ridiculously large and infinite. So let's just jump right in. This symbol, closed 2, comma, 3.1 closed. This is an infinite set, but it's an infinite set that's got a finite bound, and we'll talk about how to describe what this is. This is equal to the set of all numbers x in R, which satisfy two conditions. First, x has to be greater than or equal to 2, and x has to be less than or equal to 3.1. In other words, to draw this on the real number line, here's 2, here's 3.1, and x is trapped in between these two boundaries, but it can hit up to both. So x is any number in the world as long as x is greater than or equal to 2, less than or equal to 3.1. So let's name some things in here. For example, 2.3 is in 3.1 because 2 is less than or equal to 2.3 and 2.3 is less than or equal to 3.1. 3 is in there. Also 3.1 is in there. But 1 is not in the closed interval from 2 to 3.1 because 1 is not in fact less than or equal to 2, even though it is actually less than or equal to 3.1. 1 is not greater than or equal to 2. Okay, so that's a closed interval. Let's introduce the next idea. Suppose I give you 5, 8, and here I use parentheses instead of those bracket symbols. This stands for an infinite set, the set of x in R, such that x is strictly greater than 5, which is strictly less than 8. So the way we note this is, here's 0. We make a little open symbol for 5, a little open symbol for 8, and then we just take all the things in between them. So the idea is you have to be between 5 and 8, but you can't hit up against those endpoints. So for example, 5.5 is in the open interval from 5 to 8. So is 5.0001 is in the open interval from 5 to 8. But sadly, 5 is not in the open interval from 5 to 8 because 5 is not less than 5, even though it is less than 8. So you might want to think, by the way, what's the difference between the closed interval from 5 to 8 and the open interval from 5 to 8? They differ in exactly two numbers. They differ in 5 and 8. 5 and 8 are in the top one and are not in the bottom one. Okay, so those are the two extremes. Here's two things in the middle, which we call half-open intervals. Let's take, for example, open negative 7.1 to closed 15. You might already be able to guess this. On the open side, that means we use a strict inequality. On the other one, we use less than or equal to. This is an infinite set, it's a set of all x and r, such that minus 7.1 is strictly less than x, is less than or equal to 15. So how might we draw that? Here's an open minus 7.1. There's 0, just so we know where we are. And there's a closed 15, not to scale, and it's all that stuff in there. Okay, let's take the other extreme. So let's say, for example, closed 20 to open 20.3. This will be the set of all x and r, such that 20 is less than or equal to x is less than 20.3. Draw that on the real number line. Here's my 0. Let's see, here's a 20, and here's an open 20.3. And there's the stuff in here. By the way, a little point to make. In some sense, this seems really small, 20 to 20.3. It's really tiny on the real number line compared to minus 7.1 to 15. It's got infinitely infinitely large number of numbers in there. That's the hilarious thing about the real number line. And there's a lot of fancy math, which we won't get into behind that. We've seen closed intervals, like 2 to 3.1. We've seen open intervals, like 5 to 8. And we've seen two species of half-open intervals, like 2, 3, and like 20, 20.3. Sometimes if we want fancy vocabulary, the first of these half-open intervals is called left open. This is called right open. That doesn't really matter. Okay, let's show you one more slightly more exotic form. Suppose we write closed 2, infinity. Open there. This just stands for the set of all x and r such that x is greater than or equal to 2. Full stop. You don't have to be less than infinity because every number is less than infinity. We often draw that on the real number line. Here's 0. There's a 2, and we just take all this stuff here, kind of going off forever. This is often what we call a ray. You could also have, for example, minus infinity to 7.1 open. This is a set of all x and r such that x is less than 7.1. You get the idea. Okay, let's close by tying it into the algebra with inequalities video. We're already comfortable with the idea that if someone asks you to solve for x, and x plus 5 equals 10, you do some algebra and you solve that x equals 5. So x equals 5 is the answer. A number is an answer. Suppose, on the other hand, someone gives you the following problem. Tell me everything you know about x if the following is true. 1 is less than or equal to x plus 5 is less than 10. So notice here, a single number is not the answer. For example, if x equals 4, then 4 plus 5 is 9. 9 is less than 10. 9 is greater than or equal to 1. But 3.9 would also work. In fact, it turns out that the answer is an interval. Right? If we do a little bit of algebra, let's subtract 5 from all sides of this. If I subtract 5 from the left side, I get minus 4 is less than or equal to. Subtract 5 from the middle, I just get plain old x. That's why I subtracted 5. That wasn't random. Subtract 5 from the right, I get 10 minus 5, which is 5. So in other words, the first puzzle tells me that the answer is any x in this range. So in other words, as long as x is in the half-open interval from minus 4, closed on the left, to 5, open on the right, that's the answer. That tells me, any x in here tells me that this up here is true. Okay, that concludes our video.